Thanks, Ludovic. So let me thank the organizer. It's my first time here, but it's a real pleasure. So I'm very happy to be here. So as Ludovic was mentioning, I'm going to talk about some Stokes type theorem in Heisenberg, in Sub-Riemannian Heisenberg groups. So this is joined with Marco Di Marco, also from Padova, Antoine Juliat from Paris, and Sebastiano Nicolussi Golo, who is actually presently in Fribourg. So Marco and Antoine are somewhere around. Sebastiano is not coming, right? Okay, thanks. So let me start by recalling the classical Stokes theorem. So whenever you have a k-dimensional oriented C1 submanifold with boundary in Rn, call it M, and k-1 form, say with compact support, just to avoid integrability issues, then you have Stokes theorem, right? So you can pass exterior differentiation on the as a boundary operator on the manifold, right? So the integral on M of the differential of any smooth and k-1 form with compact support is the same as the integral of the form on the boundary. So the general question is it possible that a suitable sub-Riemannian version of Stokes theorem holds? Can we produce Stokes theorem in sub-Riemannian geometry? So we have a partial answer. So I will deal with this problem in Heisenberg groups. So I need to, in sub-Riemannian Heisenberg groups. So let me briefly introduce them. So given a number n, from 1 on, the Heisenberg group Hn is the 2n plus 1 dimensional Lie group, which is connected, simply connected and nilpotent of step 2, which is associated with this Lie algebra. Okay, so the Lie algebra is generated by 2n vectors, x1, xn, y1, yn, which are the horizontal vectors. Okay, and a further vector t. So as you know, the bracket between an element xj and the corresponding element with the same j, yj, is t. All the other commutators are 0. Okay, of course, we can always identify Hn via exponential coordinates with R2n plus 1. So 2n plus 1 is the topological dimension with some group law, which is irrelevant for our purposes. It might happen that I will put coordinates on R2n plus 1, and my coordinates are x, y, t. So x has n components, y has n components, and t is the, in my pictures, t will be the vertical direction. This is how this vector fields read in coordinates. Okay, t is the rib vector field, which is constant. Okay, so we obtain a sub-Riemannian structure by declaring xj and yj to generate the horizontal distribution. Okay, so the Heisenberg group is a particular, the easiest example of Carnot groups, which probably all of you know. So we have dilations. Okay, so we have a one-parameter family of group isomorphisms defined for a positive parameter lambda by this formula. So we scale linearly in lambda in the first 2n coordinates and with square of lambda in the vertical components. So this produces a group isomorphism. And we also fix a left invariance distance d in Hn, which is not really relevant. Okay, so for instance, the Carnot-Karateodori distance is fine for our purposes, but any good enough distance, which is left invariant, and homogeneous with respect to dilation, will work. Possibly at some point, actually at some point, I will need something more on the distance. Okay, for instance, some rotational invariance under rotations which fix the t-axis, the vertical direction. So you can think of the Carnot-Karateodori one as a good enough distance. And it's well known that the dimension, either Hausdorff dimension with respect to this distance or homogeneous dimension with respect to these dilations of the Heisenberg group, is this number, 2n plus 2. Okay, so which is the topological dimension plus 1. So the rough idea is that this vertical direction counts twice, dimension-wise. Okay? So this is our setting, the Heisenberg group, and in order even to state a Stokes theorem in this setting, we need to fix, so to decide, to understand what a differential form, an Heisenberg form is, and what a C1 submanifold is in the Heisenberg group. So before going to the statement and proof of Stokes theorem in Heisenberg, I want to fix this. So differential forms are Rumin's differential forms. So in the 90s, in the early 90s, Michel Rumin found this complex of differential forms in Heisenberg groups, actually in any contact manifold. Okay, so he was able to produce a complex of forms, which is the one you see here, which has the same cohomology as the RAM complex. Okay, so there will be 0 forms, 0 Heisenberg forms, 1 Heisenberg 1 forms, and so on. Heisenberg n form, so here I wanted to stress this passage from n to n plus 1 up to Heisenberg 2n plus 1 forms, okay? So in this first approximation, we can think of these Heisenberg forms as a subfamily, subset of classical forms with compact support, okay? Okay, so by DHK, I will denote this, a certain subset which was found by Rumin of smooth and compactly supported K forms in the Heisenberg group. So I ask the expert to forgive me, because, I mean, this is just an approximation. So the definition of this Heisenberg forms is more delicate. In particular, for forms of low dimensions, so let's say from 0 to n, they are actually not a subset of standard K forms, okay? They are rather a quotient of standard K forms with respect to a subspace. Okay, so there are arrows, and the arrows are given in this approximation that I'm giving you by the standard exterior differentiation, D, except at the critical dimension when we pass from n forms to n plus 1 forms. So Rumin found out that the correct operator is another one. It's not exterior differentiation. Is a Rumin operator, capital D, which is a quite non-trivial linear operator, which is a second order operator. So the definition of this guy, capital D, is not immediate. It involves derivatives of order 2 of your n form and produces you an Heisenberg n plus 1 form. Okay, it's pretty involved, but there are several evidences. For instance, recent papers by Kleiner, Müller, Xi. There are papers by Pierre Penseux, Franchi, co-authors, and also in geometric measure theories, there are evidences that this is the right object to consider. So there are Heisenberg forms in the Heisenberg group, as introduced by Rumin in the more general setting of complex geometry. Actually, this complex of forms can be introduced even in Carnot groups by works, for instance, of Véronique Fischer, who should arrive at some point, I guess, and Francesca Tripaldi. Okay. Okay. So this more or less answers the first question. The second one, what are C1 submanifolds in Heisenberg groups? So there is a now quite established good theory from which is essentially due to Franchi, Serapioni, and Serracassano in the last 20 or 25 years. And exactly as in Rumin's complex, these spaces are defined in two different ways. So there is a certain definition which works for forms of low dimension and another definition for forms of low codimension, okay, from n+1 on. The same is reflected in the definition of intrinsic C1, C1H submanifolds, okay? So we say that a subset S of the nth Heisenberg group is a C1H submanifold, is an intrinsic C1, a submanifold which is C1 from the intrinsic viewpoint of dimension k if the following happens. So first definition works for submanifolds or low dimension. This is pretty easy. We say that so a C1 submanifold, an intrinsic C1, a C1H submanifold of dimension k less than n is simply a Euclidean C1 submanifold which is tangent to the horizontal distribution, okay? So for instance, in dimension 1 you have horizontal curves, C1 curves, okay? In general you have surfaces which are tangent to the horizontal distribution. It's well known that such guys exist up to dimension n, okay, and not of dimension n+1 or higher. Okay, what happens? What is the definition of intrinsic C1 submanifold of high dimension? Okay, so when k is greater than n+1, C1H submanifolds are defined as level set of functions f from Heisenberg. Okay, of course, this definition should be understood locally, okay, around points of S. So locally, we can see S as the level set of a function from Heisenberg to, so this number is the codimension of the submanifold, okay? So that the horizontal derivatives of f are continuous. So f is C1H. We will say that f is C1H. It has continuous horizontal derivatives. Of course, these objects should be understood in the sense of distributions. And also, we require that now this matrix, this continuous matrix valued function has maximal rank at all points, okay? Which means that for every component fj, when we compute of f, when we compute the horizontal gradient, we get a vector which should be understood somehow as a vector which is normal to S at the point, and these normals are linearly independent. Okay, so let me say a few further words about the definition in this second case. So when the dimension is greater than n+1, so we are taking the level set definition, these level sets can be fractal, they can have fractional dimension. This was proved by Kirchheim. So an example was shown by Kirchheim and Serracassano. Still, such an object has some good properties from the intrinsic viewpoint. For instance, when you perform a blow-up procedure at a point of your level set S, what you get is always a vertical k-plane. So at small scales, your level set S is close to a vertical plane of dimension k. By vertical, I mean that it contains the direction t, the vertical direction t, and in fact, it's precisely, okay, when you identify Heisenberg and its Lie algebra, its tangent space. So this vertical k-plane is the orthogonal to these guys, okay, to the candidate normals that I mentioned before. Of course, the blow up is with respect to intrinsic dilations and left translations, okay? So the blow up is you move the point by left translation on the origin and then you blow your set S according to intrinsic dilations, okay? So here we have a normal object, okay? When we have a normal, we can define a tangent, right, as the orthogonal to the normal, okay? So at some point, this horizontal tangent k vector, THS, so the Heisenberg multivector tangent to S, is defined as the unit multivector associated with the blow up, okay, with the vertical tangent plane, okay, with the normal to these normals. Of course, this is defined up to a sign. Okay, and also pay attention to this terminology because this horizontal tangent vector is in fact vertical, because as it contains the direction t. So this horizontal might be sometimes misleading. Great. Now we have forms, Riemann's forms, and some manifolds. So the goal is we are interested in integrating k-forms on intrinsic C1 k submanifolds, okay? Provided they are oriented. So oriented means that the tangent, in particular this guy, can be chosen in a continuous way. I mean, okay? Remember that here we have two possible definitions. Okay, so integrating a form on a submanifold is pretty easy in case if you are dealing with some manifolds of low dimension. So when k is less than n or equal to n, everything here is classical, right? Omega is a smooth form, S is a C1, Euclidean C1 submanifold, so this is classical. The problem is when k, your dimension, has high dimension, so greater than n plus 1 or larger, okay? Because I told you that it can be a fractal from a Euclidean viewpoint. So so this guy in principle is not well defined. Nonetheless, it was proved that when S is also Euclidean C1, so that this guy is well defined, then integrating omega on S is the same as computing the following integral. The integral on S of what? Of the pairing, the duality pairing between omega and the horizontal tangent to S with respect to this measure. So this is the k plus 1 dimensional Hausdorff measure. Actually, for the expert, this is the spherical Hausdorff measure. Still, one of the good properties of these submanifolds when k is greater than n plus 1 is that they have integer intrinsic Heisenberg Sub-Riemannian dimension, which is k plus 1. Again, there is somehow a vertical direction which counts 2. Okay, so the topological dimension is k, but the Hausdorff dimension is k plus 1, which is integer, even if the Euclidean dimension might be fractionary. Okay, so Magnani and co-authors, Francesca Corni, but even Franchi Serapioni, Serracassano, and partly also ourselves, so they showed that whenever you have a submanifold S, which is Euclidean C1 and without characteristic points, so to say, okay, which is also intrinsic C1, then this integration corresponds to this integral, okay? And now this object makes sense, up to a constant. The constant depends only on nk and your distance d that was fixed at the beginning. The CC1 or essentially any distance you need. So here is where you need your distance to be somehow rotationally invariant in order to have this constant. In any case, now this object makes sense also for C1H submanifolds, right? Because so this Hausdorff measure perfectly makes sense. This object is well defined and continues on the manifold. So we can define the integration of omega on S in this way with this constant, which is important to, I mean, in order to have this object to be the classical one when your surface is also Euclidean smooth. Great. Now, we have some manifolds, we have forms, we can integrate forms on some manifolds. In order to state a Stokes theorem, we need to introduce manifolds with boundary. Okay? So, for me, a manifold will be somehow an open manifold, okay? And my definition of boundary is the following. So we take the topological closure of the submanifold, okay, which includes the boundary, and we subtract so the interior, the relative interior of S, okay? And we call this the boundary of S. And we say that, so this definition is, I mean, works for both low dimension and high dimensional cases. So we say that a submanifold S in Heisenberg is a k-dimensional submanifold with boundary, with C1H or intrinsic C1 regularity if, well, of course, we need S to be a C1H submanifold of dimension k. Of course, we need the boundary defined in this way to be a C1H submanifold of dimension k minus 1. Okay, this of course is not enough because, for instance, I mean, even in classical Euclidean or Riemannian geometry, you could take a submanifold S, okay, maybe a surface, remove a curve gamma, okay. Now if from S we remove a curve gamma, we are left with two separated components of F's, right? And they fulfill these two definitions, right? So in a sense, a submanifold with boundary should be either this side or the other side of this picture. So we need to introduce a condition which excludes, for instance, a situation like this, that forces us to consider only one of the two components. And this is a possible, I mean, definition, okay. So the definition, so let's read it. For every point on the boundary, we can find a neighborhood, so locally. Locally, we can locally around points of the boundary. Okay, so imagine this is the S, this is the point P, and let's say that S stays on this side. So we want to be able to extend S a little bit around P, okay, to a submanifold S prime, so in a neighborhood this would be S prime, so that when from S prime we remove S and its closure, then we will always see something more, okay? So the idea of that definition is that around points P on the boundary, we are always able to extend the submanifold a little bit, okay? So that the boundary is, so S can be extended around points P of the boundary a little bit to get locally a submanifold S prime. So S prime would be something like this. And essentially the boundary is dividing S prime into two components, one of which is S, okay? There are reasons to choose this definition, which maybe is not the first one you would imagine, right? So in classical geometry, a submanifold with boundary would be a C1 image of a, for instance, the closed half space, okay? But if you think a little bit and you use a little bit of Whitney extension theorem, then you realize that this forces you to have a little bit of an extension property close to points of the boundary, okay? So we will need this property that submanifolds with boundary can be extended in a C1, intrinsic C1 way around points of the boundary. Okay, and as you can imagine, when S is oriented, okay, it induces in a canonical way an orientation on the boundary. This is quite simple, so I will take it for granted. Eventually, you can state a Stokes theorem in Heisenberg groups and maybe give you some idea about the proof. Okay, so what we were able to prove is that whenever we have an oriented k-dimensional submanifold with boundary S with intrinsic C1 regularity, then we have a Stokes formula. So when we integrate on S the differential of any Heisenberg k-1 form with compact support, so this is the same as integrating the k-1 form on the boundary of S. So here I use this symbol dc, which stands for Rumin's differential, right? Which is either d when we are considering an arrow which is not at the critical level, or capital D when we are passing from, so when k is n plus 1, so omega is an n form and its differential is an n plus 1 form, Heisenberg form. Okay, so before starting with the proof, a few remarks. The first one is that the theorem is pretty easy. It's essentially classical Stokes for some manifolds of low dimension because everything is C1. Actually, there is something to check. So this comment is probably for the experts, so for people who knows the definition of Rumin's complex. So I told you that, in the lower dimensional part of Rumin's complex, these spaces are not exactly a subspace, but rather a quotient of classical of de Rham's K-forms. So what you need to check, even in this definition, is that, right, so this omega is not a classical form, it's rather an equivalence class. So we need to check, so there was something to check already at this level, that this integral does not depend on the representative in the equivalence class. This can be done, okay? And in the same way, the idea here is to use classical Stokes, right? So this is classical exterior derivative, but we need to check that, so there is something to check even here, due to the fact that omega is not really a classical form, but rather an equivalence class. In any case, it's not difficult, okay? More complicated is Stokes for submanifolds. So the true problem is Stokes for submanifolds of high dimension, k, n plus 1 or more. Again, there is a case where the theorem, Stokes theorem, is quite easy, because now it's true that when S and its boundary is not just a a submanifold with boundary with respect to the intrinsic geometry, so a C1H submanifold with boundary, but also C1 submanifold with boundary, then everything is again classical Stokes, okay? And that's essentially because we have this formula, right? So the definition, so this guy is the classical one. The integration is the classical integration of forms. So it's so in the setting of remark 2, Heisenberg Stokes is really classical Stokes. So we have Heisenberg Stokes when S is not just C1H but also Euclidean C1. Why do we need k greater than n plus 2? The point is that we have to avoid the case k equal to n plus 1. Why? Because this is the case where when Rumin's differential is not standard exterior derivative. It's rather those complicated second order operator, capital D. So in this case, I would say that Heisenberg Stokes is almost easy if you ask S to have further regularity, Euclidean C1 regularity again. Why? If you unravel the definition of capital D of this operator, then you see that capital D has this form. It's the exterior differential not of omega, but of omega plus some vertical stuff, okay? By vertical, so what is vertical stuff? It's some form, of some n form, okay, which one can compute by taking derivatives of omega, okay? Remember that capital D was a second order derivative and was a second order operator, and this vertical stuff is something which comes after applying a first order operator to omega. But what's the property that we have, that one of the properties of this vertical stuff? So, okay, now if you buy this formula for capital D, you can use classical Stokes to move the differentiation on S, so to transform the integral on the boundary of omega plus vertical stuff. And now this stuff, so I called vertical this stuff because if you take it and you watch it, you realize that it's orthogonal to horizontal multivectors, to horizontal n vectors. So in particular, when you integrate it on the boundary of S, which is Legendrian, it's an horizontal submanifold. Remember, in this case, right, we have two different, so the submanifold S itself is defined as a level set, but its boundary is an horizontal n-dimensional submanifold. And since it's horizontal, when you integrate a vertical stuff, it gives you 0. And that's the reason for which we have Stokes. So summarizing, this theorem is essentially classical Stokes in two cases. Either when we are considering the low dimensional case, or when we are considering the low codimension, the high dimensional case, k from n plus 1 on, and the submanifold S is also Euclidean C1, is also Euclidean regular. We want to prove, so what we mean is proving Stokes for, in the high dimensional case, for general submanifolds of class C1H, right, which can be fractal. And the idea will be to work by approximation, okay? So the idea will soon be split into two cases. This first case and the critical case k equal n plus 1. But in both cases, the idea is to approximate S by a family Sj of Euclidean C1 submanifolds, okay, in C1H, so to say. So approximating in C1H means that your sequence is converging uniformly and the tangents also are converging uniformly. The horizontal tangent are converging uniformly, because if you are able to do so, then you can perform these pretty easy computations, right? So we start from the integral on S of the derivative of omega, the exterior derivative. We can see it as a limit on the integral of the same form on Sj, on the approximating sequence. This is because the tangent to Sj are converging to the tangent of S, right? So here we use classical Stokes, or if you prefer, I mean, remark 2 and remark 3, okay? But now we have a C1H, so the boundaries are converging in C1H to the boundary of S, if we are able to perform this. And so this integral is converging to this guy, okay? Now, so the goal is to approximate S, and in fact, the core matter of the proof is not just proving Stokes, it is to approximate any S in C1H by smooth, Euclidean smooth submanifold with boundary Sj. Okay, so when the dimension k is not the critical one, so it's m plus 2 or more, in this case, both the submanifold and its boundary can be seen as level sets. And all in all, producing these approximations as Sj amounts to proving this equivalent definition of C1H submanifold with boundary, okay? So when we are not in the critical dimension, we can prove that a subset S is a submanifold with boundary if and only if we can write it as in this way. So we can find functions f1, fh plus 1, which are intrinsic C1, and they are defining functions for the boundary, ds. Remember, ds also can be seen as the level set of a function f1, fh plus 1. So h here is the codimension of S, so h plus 1 is the codimension of its boundary, okay? So an equivalent definition is we can find f1, fh plus 1, which are defining functions for the boundary, okay? So in particular, the gradients, the horizontal gradients are linearly independent, and the submanifold S itself can be seen as the level set of f1, fh, plus the portion of points where fh plus 1 is positive, okay? So if you want, if you remove this condition, the first h1s are defining S prime. Remember in the definition of submanifold with boundaries, so these conditions define S prime. This further condition defines somehow one portion, one component of S prime, which will be S, which is separated from the other component from the zero set fh plus 1. Okay, and this is an equivalent definition of being a C1H submanifold with boundary, at least in this case, even though the proposition shows you only one implication. It's clearly an equivalence. And now it's quite, once you have a tool like this, it's not so difficult to produce the approximation Sj. What could you do? Well, these functions are only C1H, but there are tons of ways of approximating them by smooth functions, by approximating them in C1H by smooth functions, f1 epsilon, fh plus 1 epsilon, okay, which are conversing in C1H, and then you can define, I mean, you're approximating submanifolds by simply taking the 0 and upper level set of f1 epsilon, fh epsilon, and so on. And in this way, you produce what you need. So once you have this tool, it's enough to approximate the defining functions, and you get almost for free the approximating submanifold. The delicate case is at the critical level, because at this point you have your submanifold, which is defined as a level set, and the boundary, which on the contrary is a Legendrian, an horizontal submanifold, right? Again, we want to argue by approximation, but let me stress that the argument is easier when n is 1. So in the first Heisenberg group, which is R3, when you consider surfaces, so two-dimensional submanifolds, whose boundary is an horizontal curve, the approximating argument is quite easy. And in fact, it was discovered a long time ago by Franchi, Chu, and Tesi. So let me maybe draw a picture. Okay. So again, this is a C1H submanifold. Where did I put? Okay. Okay, so this is only C1H, so let me draw it like this in order to stress the fact that it's not a regular subman. So this is S. Its boundary ds is a horizontal curve. Okay. And we know that S can be extended, right, to S prime, okay, which is again maybe a fractal, so a not so regular object, across the boundary of S. Okay, so we consider, at least locally, everything can be, I mean, the problem is local, okay? So extend S to a C1H subsurface S prime, okay? And then we have by now many techniques to approximate S prime by smooth objects, okay? Smoother objects, call them, how did I call them? Sj prime. Okay, so they are approximations of S prime. And now on Sj prime, we might decide to consider a horizontal curve which somehow is close to ds, and okay. And in this way, we produce, so we consider one side of Sj prime, call it Sj, right? It will have as boundary this horizontal curve. So the horizontal curve allows you to separate Sj prime into two components. One of them will approximate S together with the boundary, okay? So the idea is to cut Sj prime, so an approximation of S prime, along a horizontal curve passing close to the 2 points of the boundary of S, okay? So here the computations are not big. However, this technique cannot immediately be extended on higher dimensional Heisenberg groups. The point is that if we want to reproduce these arguments, so now S is, so for instance in H2, S would be 3-dimensional, the boundary of S would be 2-dimensional, right? So we could extend to get S prime, also 3-dimensional, but now we would need to produce on S prime, or sorry, So we approximate S prime, but so the idea would be, okay, the argument would go like this. We produce S prime, which is three-dimensional. We could approximate it by Sj prime, also three-dimensional, and now we would like to cut Sj prime into two components by using a horizontal submanifold of dimension 2. But to do this, somehow we would need, for the horizontal distribution on Sj prime, to be integrable. And this is something that in general we cannot guarantee. So there is no reason why in this approximation the horizontal distribution is integrable. So in fact, we had to produce a different argument, which maybe I will try to draw here. Okay. So the idea would go like this. We produce the approximating family Sj in such a way that they have the very same boundary as S. Okay? So again, S is something which is maybe not so smooth. Okay? But its boundary, ds, we know is so this is n plus 1 dimensional and this is n dimensional, and we know that it's Euclidean C1, right? And horizontal. So in particular, it's transverse to the vertical direction t. So we first produce a Euclidean C1 submanifold S tilde with the same boundary, and this can be done simply by extending the boundary. So S tilde is the red submanifold there, okay, which is simply taking the boundary and extending it in by a vertical invariance, right? So this S tilde is foliated is ruled by vertical lines, which are transversal to the S. Okay. Now look at S. We know that we can. So this is C1H, and we already know how to smoothen it, so how to approximate it in C1. Okay, so here the picture is not so good, because I want this, okay. Okay, by some submanifold that I called sigma j, okay, so sigma j is an approximation of S. And in this approximation, we don't care about the boundary of Sj. And eventually here, when we get close to the boundary, we are able to interpolate, so to attach sigma j at some point with sigma tilde by some green submanifold, okay? This is something that you can do. So let me zoom the picture, hopefully. Okay, so let's work. So let's look from this side so that the boundary of S for me is like a dot and a line. So I produced S tilde in a vertical invariant way, and S, on small scales, we know that the blow up of S is a vertical plane, and as a matter of fact, what turns out is that S becomes very close to the red submanifold that I produce here. So when we approximate it, the approximation will stay somehow close to S tilde, and now we develop techniques to glue the two submanifolds together, okay? So geometrically, this is the picture. which is maybe a bit small, so I apologize with people over there, but thanks for your attention.
Thank you. Are there any questions or comments? Nashwa?
Thank you very much.
Thank you.
Please, could you please give us an example of C1H submanifold?
Okay.
Because the most simplest.
Oh, the simplest is half of a vertical plane. So in the first Heisenberg group, but it's pretty trivial, right? You can consider a vertical plane, right? Cut it with a horizontal line. Okay, and that's a C1A submanifold with boundary. If the question is something which is not Euclidean C1, that's pretty tough. Even the examples we have are a bit hard. Although I have a paper where we show how to produce submanifolds like this with lesser regularity, but there are. Also, let me stress the fact that there is also somehow some topological constraint. So these results that I presented in Heisenberg should be understood in a local sense, right? Because it's pretty difficult to produce, for instance, maybe impossible, to produce C1H submanifolds whose boundary is a horizontal circle. They will always have some characteristic points, right? Yeah. If you want everything to be compact, that's not possible, I guess. There are topological restrictions. Global examples you can produce, like half a vertical plane. But in fact, the result that I presented, so I wanted to avoid localization, so put yourself in an open set omega of Heisenberg. All of these arguments should be understood in a local sense. Thanks for the question.
So in case the H1,
yeah.
show that the torus is the unit.
Yeah.
Unit, so hypersurface.
Yeah.
But it has no characteristics.
Yes. Yes, yes, yes. The results are local, okay? So in an open set, and you should consider forms which are supported in that open set, and there you have an integration, a Stokes theorem. That's how you should interpret this. Thank you.
Other questions or comments? Yes, Enrico.
Thank you, Davide. I have a similar question. So, but in the other case, so if we just want to understand how restrictive is to have manifolds with boundary. Okay? So, if we have a K Heisenberg submanifold and fix a point up to restricting to an open set, can I assume that the boundary is also a K-1 surface?
Say it again, what do you have?
We have a K-dimensional submanifold. We have a point in the manifold.
Which regularity?
C1H.
Okay.
Mm-hmm. Is it true that up to intersecting with a small enough open set, then I can make the boundary C1H K-1 dimensional submanifold?
Oh, you mean, so we have a submanifold, okay. So let me see if I understood your question. We have a submanifold as, we fix a point.
Yeah.
Okay, so we take like a ball something.
Yeah, I ask if there is, maybe a ball is too restrictive. I'm asking, is there an open set in such a way that now the intersection become a C1H submanifold with the boundary?
Okay, so you mean this to be C1H? No idea. No clue.
Because they could, this C1H submanifold with boundary could be very restricted.
Yes, if you think it globally, yes.
But even locally.
No. My point was, locally you can produce these guys.
Yeah, but this is going from the boundary.
And if you consider forms which are compactly supported on an open set like this, then you have Stokes.
Yeah, but see, you started with the boundary and then you fill it with something. And now I'm asking the same. You have the filling. Can you create a boundary that's C1H?
I don't understand.
In your example, you were starting with something that was the future boundary, right?
Something that was?
Was the boundary at the end.
Yeah.
Right? Now I'm asking the end. You have the filling and asking, is this filling the boundary of something regular up to restricted? Right? Because it could be that you are only studying, being very pessimistic, right? It could be that you are only studying the surfaces that are vertical.
No.
Vertically foliated.
No. You can always produce in an open set a situation like this, right? Okay? And then when you consider forms which are supported in this open set, okay, of course, so the point is that you probably cannot close the picture. Okay, you cannot fill this portion of submanifold with boundary, which is defined only in an open, in a bounded open set, for instance. You cannot close the picture to produce a submanifold with a boundary which is C1H, so that both are C1H. Okay. Okay, so the picture should be local. Okay. What I forgot to say is that, I mean, one of the reasons, apart from the result itself, in my opinion, this tells us that these two theories are consistent and they are the correct theories. I mean, the theory of Rumin's forms and Franchi, Serapioni, Serra-Cassano submanifolds, they are consistent and they are the correct object to consider in the picture. Thank you.
Okay, so if there are no other questions, you can thank the speaker again.